Whenever you plug something into the wall, have you ever really thought about what's going on in there? It's not as simple as just electricity. There is this hidden world of incredible technology working silently inside all of our devices that has to tame, shape, and control that raw power. Today, we're diving into that world, the world of power electronics.
And just think about this for a second. How is it possible that a tiny little component, something smaller than your thumbnail, can precisely manage the absolutely immense flow of energy it takes to spin the wheels of a 2-ton electric car? It seems impossible, right? Well, that's the kind of magic we're going to unpack today. And it all comes down to one thing: control.
All right, let's get into it. To really get a grip on how we control all that power, you first have to appreciate the challenge we're up against. See, electricity straight from the source, it's kind of like a wild horse. Unbelievably powerful, but not very useful until you can tame it.
That alternating current, the AC power coming out of your wall outlet, it's fantastic for sending electricity over long distances. But your laptop, it needs a steady, low-voltage direct current, or DC. And a battery, well, that provides DC, but then an electric motor might need high-voltage AC. The point is, they all speak completely different electrical languages.
And this is exactly where power electronics steps in. It's the technology that acts as the universal translator. It uses what we call solid-state components, which just means no moving parts, it's all based on silicon, to convert and control electricity with incredible speed and efficiency. Honestly, it's the secret sauce that makes all of our modern tech possible.
So, how does it all work? Well, this entire field is basically built on the back of some very special semiconductor devices. And today, we're going to meet the original hero of this whole story, a device that was first developed way back in 1957. It's called the Thyristor.
So let's take a look under the hood. The Thyristor's real power comes from its internal structure. It's got these 4 alternating layers of silicon, which we label P and N. And this clever little PNPN sandwich is what gives it all of its unique abilities. You'll see it has 3 main connections: the anode where current goes in, the cathode where it comes out, and this really important control input called the gate.
And in an electrical diagram, this is what it looks like. Now, it kind of resembles a diode, right? Which, as you know, lets current flow in one direction, but it's got that extra little line for the gate. And let me tell you, that gate is everything. It's the handle, it's the trigger, it's the key that lets us control all that power.
So what is it really? At its heart, a thyristor, which is also called a silicon-controlled rectifier, or SCR, is just an electronic switch. But oh, it is a very, very special kind of switch. For one, it only lets current flow in one direction. But most importantly, it stays completely off until we tell it to turn on using that gate.
Okay, I know this graph might look a little intense at first, but trust me, it tells the entire story of the thyristor perfectly. It basically plots the voltage across the device against the current flowing through it. And in doing so, it reveals its 3 very distinct personalities, or what we call modes of operation.
Okay, so first up is reverse blocking. If you try to send current through it backwards, it just says no. Simple as that. It's an open switch. Second is forward blocking. Now this is the really clever part. Even if you apply voltage the correct way, it still says no. It just sits there in a ready state, waiting for the signal. And finally, number 3, forward conduction. Once it gets that signal, bam, it flips to an on state and lets current surge through like a closed switch. So the all-important question is, how do we get it from that waiting state, that forward blocking state, to the on state? How do we flip the switch?
Well, it turns out there are a few ways to do it. You could just hit it with a massive forward voltage and force it to turn on. But that's really risky and you can damage the device. You could also use heat or even light if you have a special kind of thyristor. But really, there's one method that is, by far, the best.
And that method is gate triggering. As the source material puts it, this is the simplest, reliable, and efficient method. It gives us precise, predictable control. And this graph shows you exactly why it's so brilliant. Just look at this. A tiny little bit of current applied to that gate dramatically lowers the main voltage you need to flip the switch on. It's literally like using a small key to unlock a massive floodgate. A tiny, low-power signal can precisely control a huge, high-power flow of energy. It's amazing.
And here's another really cool feature. Once you trigger it, it latches on. You only need to give the gate a little pulse, just for a moment. Think of it like a mechanical light switch that clicks into place and stays there. As long as enough current is flowing through the main circuit, above a level we call the holding current, it will stay on all by itself. You don't have to keep that gate signal on.
Okay, so we have this incredible controllable switch. What can we actually do with it? Well, this is where the magic really happens. We can use groups of these switches to make electricity shapeshift into pretty much any form we need.
The first and maybe most common application is a rectifier. A rectifier's whole job is to take that wavy back and forth AC from the power grid and turn it into the one-way DC that powers pretty much all of our electronics, from our phone chargers to our computer power supplies.
Here we've got a classic bridge rectifier. See those 4 thyristors? They work in pairs. So as the AC current flows in, one pair grabs the positive part of the wave and sends it through. Then, when the current reverses direction, the other pair kicks in, takes that negative part of the wave and flips it upright. And what you get at the end is this bumpy but purely positive DC output. Next up, we have the chopper. So, what if you already have DC power, say from a battery, but you need to change its voltage? Imagine controlling the speed of a power drill or a fan. You don't just want on or off, you want all the speeds in between. That is exactly what a chopper is for. A chopper uses a thyristor to switch the main DC source on and off thousands of times every second. By controlling exactly how long it's on versus how long it's off, it can control the average voltage the motor or device sees. So, more on time means a higher average voltage and more speed. Less on time means a lower voltage and a slower speed. It's that simple. And finally, we've got the inverter, which, as you can probably guess, does the exact opposite of a rectifier. It takes DC power, maybe from a solar panel on your roof or the huge battery pack in an electric car, and skillfully switches it back and forth to create the AC power that we need to run our home appliances or those powerful AC motors.
So these devices are obviously incredibly powerful, right? They're handling huge amounts of energy. But with that great power comes great vulnerability. These tiny titans are actually pretty sensitive, and they need to be protected if we want them to work reliably.
They face a few major threats. First, overvoltage. Sudden voltage spikes from things like lightning or just switching big motors can damage them or even trigger them by accident. Then there's overcurrent. A short circuit can cause a massive surge of current that can destroy the device in milliseconds. And of course there's heat. Just heat is the enemy. Handling all that power generates a lot of heat, and if you can't get it away from the device, it will literally cook itself.
And this is why a real-world power electronic circuit is so much more than just the thyristor itself. It's a whole system. You'll see special circuits with things called snubbers and varistors to clamp down on voltage spikes, super fast-acting fuses for overcurrent, big heat sinks for cooling, and even protection for the delicate gate circuit itself. Because in this world, reliability is absolutely everything.
From the charger for your phone to the massive power grids that run our cities, power electronics are the invisible, indispensable technology of our modern age. And as we push for more efficient solar panels, faster electric cars, and smarter energy grids, the demand for better, faster, and tougher power electronics is only going to grow. The quiet revolution that was started by these tiny titans, well, it's far from over.